This video presents supplementary material for a research entitled, A Model Predictive Capture Point Control Framework for Robust Humanoid Balancing via Ankle, Hip, and Stepping Strategies. To demonstrate the balancing performance of the proposed method, a Myeong-Ju Kim simulation video is presented. This video demonstrates an experiment in Section 6b, where a robot successfully balances against external disturbances. In the experiment, the robot experiences external pushes of 48 Newton-sec and 100 Newton-sec, applied in the negative x and y directions respectively. The robot overcomes these disturbances using a combination of ZMP control, CAM control, and footstepping control. Next, in the experiment presented in Section 6c, the robot successfully maintained balance and navigated forward without falling over a total of 4 unexpected objects using the proposed method. The first and second objects were overcome using ZMP and stepping control. For the third and fourth objects, CAM control was additionally employed. Next, the balancing performance of the proposed method is compared to the methods based on the combinations of each strategy. In this experiment, we applied the maximum external forces that the robot could withstand when using each method to the robot walking in place. As depicted in the video, it can be observed that when the proposed method is employed, the robot overcomes the largest external forces in all directions: forward, backward, left, and right. In this video, the balancing performance is compared between the QP-based CP controller proposed in reference 39 and the proposed method. In this experiment, external pushes in the forward, backward, left, and right directions are applied to a robot while it is either walking in place or in a forward walking state. When the same external forces are exerted on the robot, our method successfully maintains balance. However, when using the method described in reference 39, the robot fails to maintain balance and falls over. To ensure the reliability of the proposed method, we conducted real robot experiments in addition to dynamic simulations. It demonstrates the robot's ability to maintain balance despite being subjected to external pushes in the negative x and negative y directions, measuring 46.8 Newton-sec and 94.4 Newton-sec respectively. Just like in the simulations, the robot overcomes the disturbances through the implementation of ZMP, CAM, and stepping control. In light of the simulation results, where the robot overcame objects, the real robot exhibited a similar outcome. Despite encountering 3 unexpected objects during its forward walking, the robot successfully utilized the proposed method, enabling it to maintain balance. A comparative experiment was conducted using a real robot with the reference 39. When implementing the method described in reference 39, the robot withstood impulses up to 35.6 Newton-sec and 68.8 Newton-sec in the x and y directions respectively. However, beyond those magnitudes of impulses, the robot failed to maintain its balance. In contrast to our method, during the experiment in Section 6i, the robot encountered difficulty surpassing the 2.5 cm object despite repeated attempts, ultimately resulting in a loss of balance. Lastly, repeated experiments were conducted to assess the reliability and repeatability of the proposed method. The video on the left showcases a repetition of the Section 6h experiment, while the video on the right demonstrates an experiment conducted to evaluate diagonal disturbances. Next, despite encountering various unexpected objects, the robot consistently overcame each object in multiple experiments and successfully completed the walking task. Thanks for watching this video.